Hello, everyone. Today we're going to solve a geometry problem that combines circles, a square, and a really nice chord theorem at the end. Here's the situation. We have a semicircle with diameter AB. Inside that semicircle, there's a square sitting in the corner at point O, and we're told the area of the square is 5. From that information alone, we want to find the length of BC. So BC is a chord from B to another point C on the semicircle, and we're trying to compute that length. Before we start calculating anything, pause the video. Ask yourself, if the square has area 5, what does that immediately tell you about its side length? And how could that connect to the radius of the semicircle? Okay, let's walk through it slowly. First key observation, the area of the square is 5. So the side length of the square must be the square root of 5. That's our first important number. Now look at triangle OED inside the semicircle. Both horizontal and vertical sides of the square are square root of 5. So if we compute OE using Pythagorean theorem, we get OE squared equals square root of 5 squared plus square root of 5 squared. That gives 5 plus 5, which is 10. So OE equals square root of 10. And since OE is a radius of the circle, that tells us the radius of the semicircle is square root of 10. That's big. Now we know the full diameter AB is twice that, but more importantly, we know OB equals square root of 10 as well. Next step, we look at triangle OBD. We already know OB is square root of 10. We also know OD is square root of 5 because it's a side of the square. So using Pythagorean theorem again, BD squared equals OB squared plus OD squared. That's 10 plus 5, which equals 15. So BD equals square root of 15. Now here's where the problem becomes interesting. Up to now, everything was straightforward geometry, but to find BC, we need something extra. So we imagine the full circle, not just the top semicircle. We extend the diameter vertically to complete the circle and draw a full vertical chord through D. Now we can use the intersecting chords theorem. That theorem says when two chords intersect inside a circle, the product of the segments of one chord equals the product of the segments of the other chord. So at point D, we have dB times dC equals dG times dH. Let's compute dG times dH. dG is square root of 10 minus square root of 5. dH is square root of 10 plus square root of 5. Multiply those together. That's a difference of squares. Square root of 10 squared minus square root of 5 squared. That gives 10 minus 5, which equals 5. So dG times dH equals 5. That means dB times dC equals 5. But we already know dB equals square root of 15. So dC equals 5 divided by square root of 15. Now we're almost done. BC is made of two pieces, BD plus DC. So BC equals square root of 15 plus 5 over square root of 15. Let's simplify that expression. Combine over a common denominator. That becomes 4/3 times square root of 15, and that is the length of BC. So from just knowing that the square's area is 5, we were able to find the radius, compute BD, use intersecting chords, and find BC. If you enjoyed this one, go ahead and like the video. If you guessed we'd use intersecting chords at the start, comment below. And if you enjoy problems that combine algebra with circle geometry like this, make sure to subscribe. All right, thanks for watching, and I'll see you in the next problem.